Hey, hey, hey. Yeah, okay. I'm not sure. It's very difficult to find, right? Yeah. The other one, this one, the problem is the switch is bad. Better, I suppose. I will try. Hello.
Hello. During the session, I want to know how do I check the time? Is there something?
Ah, it works. Okay. Let's see. Anyway.
C'est pas le deuxième, moi. C'est pas le deuxième.
Les transparents, ils sont là, ok?
Voilà.
Slide of the second photo here.
Yes.
Not here, but definitely has a substitute. Oh yeah, okay. Start.
Good morning. Welcome to the session Lattice Algorithms and Cryptanalysis. The first talk is log S unit lattices using explicit Stickelberger generators to solve a prox ideal SVP by Olivier Bernard, Andrea Lesavouret, Teung Hui Nguyen, Adeline Roux Langlois, and the talk will be given by Olivier.
Okay, thank you for the introduction, and thank you for attending. So, as announced in the M'entendez? Yeah, okay. So, as announced in the title, we are going to. So, yeah, the sliders now are not going. Okay, thank you. So as announced in the title, I'm going to talk about the context of cryptanalysis of ideal SVP. Then I will present the principle of S-unit attacks, and in particular twisted PHS. And I will talk about details about our work going towards medium dimensions. So let me go through some definitions. So Formally, a lattice is a discrete subgroup of R to the n. So you have a nice picture, well, hopefully nice, in for n equals 2. And you can have a good basis and bad basis. The orange one is good one, and the purple one is probably a bad one. And the shortest vector problem is NP-hard problem in general. It's asking you to find the shortest vector of the lattice. And you can relax this by allowing some approximation factor. And it's believed to be still hard for polynomial approximation factor in the dimension. So, okay, for efficiency reasons in cryptography, we use algebraically structured lattices. So this means that yeah, you can have a grasp of what is the structure graphically here, but it inherits of the multiplication in the number of fields. So you have an additional operation in your lattice, and you can also multiply lattices between them. And so the question is, can we use this structure to better solve ideal SVP? I mean, to better solve the shortest vector problem in these lattices, in these particular lattices. And the answer was no for a long time. But in 2014, there was this quantum algorithm computing number theoretic objects in a quantum polynomial time, such as S-unit class groups. These problems are classically hard to solve and sub-exponentially in the discriminant of the field. And this is induced a long series of cryptanalysis works, and I hope that I didn't forget anyone, but if I did, please write to me. So, okay, I'm going to give a picture summarizing this cryptanalysis, this series. I'm going to make some shortcuts, and I will complete this later in the conclusions with recent advances. So first, in the unstructured case, you have this Corkin-Zolotarev trade-off, which is telling that if you are happy with exponential approximation factor in the dimension, then you can do it in polynomial time. But if you want better approximation factors, typically a polynomial one, then you will have to pay for an exponential time in the dimension. So this is known as Schnorr's hierarchy, and we are going to try to beat this hierarchy for ideal lattices. Okay. So the first generic for all lattices and a wide range of fields, which was beating the Schnorr's hierarchy, is the CDW algorithm by Kramer, Dukas, and Veselovsky. So it was in 2017, and the journal version is extending this in last year. And this uses Shor-Stickelberger relations, and this says that if you have a quantum computer, then in polynomial time you can probably find a sub-exponentially small vectors in your lattice. So this was the first bridge into Schnorr's hierarchy. Okay. Later on, there was this proposal by Pelé-Marie and Rose-Télé, which was extended in twisted PHS. This is maybe known now as S-unit attacks. So the formalism was given in it was underlying PHS and explicitly used in twisted PHS. And this applies to any fields, but I'm only giving here the picture for cyclotomic fields. But you have to pay for an exponential precomputation. So this means that you can do an exponential precomputation on a fixed field, and then you will have for each challenge a better trade-off than Schnorr's hierarchy. Even classically, you have this zone here, which you are beating the Schnorr's hierarchy, and polynomially you have a whole range of other trade-offs. And okay, so the question is now how threatening are these S-unit attacks in practice? So this is a little bit paradoxical because we are imagining that we have a quantum computer, and we are going to ask, okay, is this really bad for ideal SVP problem? In particular, in twisted PHS, we use another encoding of the problem, and this gives astonishing results in practice. So I think the main two experimental results that are surprising is first, it seems that the log S-unit lattice is very orthogonal. You can see it on this very special shape of the Gram-Schmidt log norms. And the second one is that the approximation factor that we obtain here in orange, so this is the very lowest line here. This is a logarithmic scale, so there is a huge difference between the top curve and the lower curves. And it seems to be growing very slowly in a way that could be sub-exponential or polynomial, could be anything. But the problem is, the caveat is that it's only experiments in a small dimension, and appearances can be very misleading in this case. So we need to gather more experimental observation before we can predict anything sensible. But the problem that we have is it's really hard to compute the objects that we need in the classical world, and climbing degrees is really hard. So this is what we do in our work. So we propose, in the case of cyclotomic fields for any conductor, a construction which is a full rank family of independent S units. So I will maybe explain a bit later what it is. This is composed of two parts. So first we take what we call real S units. So you get roughly half of them, half of your whole S unit group. And so this is the remaining classical hard part, but it's in we halve the dimensions, so this is going to be easier. And we complete that by explicit Stickelberger generators. So yes, so we prove that by giving an effective formula for the index and proving an effective formula for the index in the full S-unit group. And in particular, this is an infinite index, so this proves the full rank property. And for computations, everything is going to explode and go wild. So we really need to use a short basis of the Stickelberger ideals. This will give you a small generator and a few of them. Okay, this has two applications that we develop in our paper. So the first one is to remove almost all quantum steps in the CDW algorithm. So mainly, we remove the need for the random walk in the relative class group. Yes, by using real class group relations. And we remove this CDW is a two-stage algorithm, and between the two stages, you have a quantum step for solving the principal ideal problem. But since we have explicit generators corresponding to our relations, you can just compute that explicitly. Second application is to simulate the twisted PHS algorithm in medium dimensions up to 210, and this is a huge computational breakthrough. And we are able to confirm the geometry of the log S-unit lattices is very particular, as was noted in twisted PHS. And if you want some theoretical explanation of that phenomenon, you should go and read the paper by Bernstein and Lange in 21. And this is a graph. I'm going to go back later on that. This is a graph of the approximation factors that we obtain, and you can see that here we are going to have something that looks like a sub-exponential or exponential shape when you reach meaningful dimensions. Okay, so may I explain a little bit the general principle of S-unit attacks? So you take a challenge ideal B, and you always have first a quantum polynomial step. So it can be computed by a sub-exponential classical algorithm. And you decompose B on a factor base S, so you will decompose B as a principal ideal part and a product of prime ideal in the factor base. And the fact is that all solutions to this decomposition are equal modulo multiplicative group, which is called the S-unit group. And then the aim is to find a short coset representative of this. And so the technique is quite generic. You have to use some logarithmic function, which is transfer your products into sum. And the image of the S-unit group under this logarithmic function is called the log S-unit lattice. And with when solving a closest vector problem, an approximate vector closest vector problem in this log S-unit lattice, you will obtain hopefully a short coset representative, and you hope that this is a short element of your ideal. So you can see that there are some important parameters to consider here. So the first one is probably, and the most important is probably the choice of the S-logarithmic embedding. So in twisted PHS, we use the number theoretic weights. So this allows you to make a wiser choice of relations. The second important parameter is the choice of the factor base. So you can take a very big factor base or a smaller factor base. In twisted PHS, we chose to maximize the density of the log S-unit lattice. And the last one, probably the choice of your approximate CVP oracle. So you, depending on what price you are ready to put in that. Yes. In twisted PHS, we choose to use a somewhat naive algorithm. We just use a randomized Babai's nearest plane, and in this presentation, we are also using a randomized Babai's nearest plane for our experiments. Okay, graphically, this looks something like that. You have the log S-unit lattice here. This is an hyperplane orthogonal to the all one vector. Let's take a challenge ideal B. The quantum decomposition output, you can see that you have a principal ideal part here and a product of prime ideal in the factor base. And you use your favorite logarithmic S embedding to obtain a point, the log of alpha 0 here. And now you want to find the shortest coset representative. And so all solutions are on this line, this blue line. So this is just a translation by some points in the log S-unit lattice. And we hope to find the shortest one. So we will project into the log S-unit lattice, find a S-unit such that the logarithmic S embedding of this S-unit is close to the projection. So this will give you here S equal to product of some prime in the factor base. And then you can subtract this log S to the log of alpha 0, and this corresponds to alpha 0 over S in the image pre-image space. Yes. And you hope that this is a short element in the ideal. So the hard part is now to know how efficient this is. The hard part is really the main obstruction is to compute this log S-unit lattice here. So in our work, as I said, we have this construction which is using real S-units. So you will get roughly half of them, and we have to complete that family by explicit Kuckelberger generators. And this is really how we break the Haiti barrier to get to dimension 200. And the proof is about proving this theorem. This gives the index of the of this construction in the full S-unit group, and this is not important exactly what is this formula, but we have to note that there is a huge factor here. This is a relative quark group with a huge prime in it, so this is really big, and you have a huge part here of powers of 2, and we can manage to remove them. So we will use what's called classically two saturation techniques. And this consists in detecting in your multiplicative family some combinations that are squares. And once you have detected squares, you can compute square root and integrate in your family. And everything is going to go wild, so you have to use short Stickelberger bases to unlock high dimensions in practice. So I think I don't have the time to present you what's a Stickelberger ideal. You should just know that you can represent this as a vector on rational, and you are keeping the linear combination of these vectors that have integer coefficients here. The second point to remember is that the Stickelberger theorem tells you that these elements give free relations in the class group. So you take one ideal, you take a Stickelberger element, and your resulting ideal is principal. And the third very important point to remember is that the proof is completely explicit, so you can describe and compute the generator. But even with moderately high coefficients, you will have a huge generator, so you have to start as low as possible. So yeah, this is the work with Radan Kuchera, and we showed how to extract a short basis, and we showed that in that case, the generators are really easy to compute. So experimentally, we yes, we were able to. You can see an example here for log S unit lattice of dimension 1200. This is the shape of the Gram-Schmidt log dump, so this shows that this is really orthogonal. And this is a very general phenomenon, so this confirms that there is something going on with this lattice. And second, we have this a graph of approximation factors. So our densest approximation of the S unit is the yellow points here, and you can see that there seems not for this instance. This doesn't show a catastrophic impact of this S unit attack, but this is neither reassuring because you can densify further your lattice or use other arguments and go beyond this curve. And the other point to see on this graph is that there were a lower bound for the two-stage algorithm CDW, and this is the green dots here, and you can see that in some case the twisted PHS simulation here is beating this this lower bound. So this shows the power of using a unique lattice to optimize the output all at once. So yes, it's time to conclude. So I would like to mention a recent conjecture by Bernstein, Eisentrager, Rubin, Silverberg, and Van Vrendendahl. So this is a red star here. So if I try to give the two main ideas of this conjecture, is to use a sub-exponential factor basis, so very big factor basis, regardless of the density of your log S unit lattice, and to use an enumeration-based closest vector problem oracle using many small S units. And the claim is that you can reach a polynomial approximation factor in sub-exponential time. So this is this has given rise to many debates in the community. There is no formal paper, but you have some code and description online. And maybe the main issue is that experimental evidence so far are limited to prime conductor cyclotomic fields of degree less than 42. So this might be subject to the same small dimension effect than twisted PHS. So this this leads me to my conclusion on ongoing work. So the first item is to try to densify further the log S unit sublattices to verify the evolution of the approximation factor for several orbits. And we are almost there, so I think in 1 month or two we should be able to publish what we obtain for saturating all factors of the relative class number. And the second is to build a practical simulator of S unit attacks in order to test other parameters and to try to explain better what is going on. And the fact is that this paper that I'm presenting today provided a lot of data in medium dimensions, and we should now we have to use that to support and find finer heuristics and estimation. So thank you for your attention, and if you have questions, don't hesitate to reach for me.
We have time for one quick question. Yes.
So I think many people may be wondering this, but so do this type of attack, is there any hope to extend them to, say, module lattice of rank 2, for example?
So for now, there is no reasonable proposal to extend this to modules, yes, unfortunately.
Okay. So let's thank the speaker again. Okay, so the next talk is on model unique SVP and N-true by Joël Fedorov, Alice Polemari, and Damien Stellet, and the talk will be given by Joël.
Hello everyone. I think my remote is not working. I'm sorry. Thank you very much. Okay, hello everyone, and thank you for fighting the jet lag and tiredness to come and see me at the beginning of the day. So I'm Joël Felderhoff, I'm PhD student of Damien Stellet at the ENS de Lyon, and I'm going to present you a joint work with so Alice Polemari and my supervisor Damien Stellet, which his name is on module USVP of rank 2 and N-true. So this is actually a good sequence of presentation, because at the end of the last one we asked about module lattices, and so one of the goals of the presentation is to show some gap between ideal SVP and module USVP in rank 2, which basically answer the previous question, so that's cool. First, let me present the contribution I'm going to explain in this talk. So I'm going, here module SVP of rank 1 is just a pedantic way of saying ideal SVP. I'm going to present some lattice problem, some module lattice problem that is equivalent, that we show are equivalent to N-true, which is a security assumption used in some cryptographic schemes. And we are going to show that, I lost my pointer, that this new problem, well, this problem has a good property, which is a reduction from worst case to average case. So first, some definitions. So N-true was proposed in '96 by Hoffstein, Pfeiffer, and Silverman. And so here we are going to work on polynomials. So every element of every lattice I'm going to present are polynomials modulo x to the n plus 1 for n to the power of 2. The size of an element is the L2 norm of the polynomial. And N-true asks, if I give you some polynomial h, which is equal to f over g for some small f and g, to find back f and g. So this problem has been proposed, as I said, in the 90s. It has an advantage over other cryptographic assumption because it leads to very small keys. So basically, in that problem, the public key will be H, the secret key will be F and G, and so F and G are rather small. It leads to fast encryption and decryption algorithm, and it's quite old, so it has been studied a lot. So for example, we know basically what modulus Q to take in order to be secured and stuff like that. Well, actually, we know what modulus Q not to take to not be insecure. So this problem seems a bit ad hoc, like I give you polynomials which are equal to ratios of polynomials over modulo, etc. So the question is, can we relate this to lattice-based cryptography? The fact is, yes. If you want to analyze this problem, you can define a module, which is basically the set of, if I give you H, the set of all possible secret key. So the set of every F and G such that F times H is equal to G mod Q. This is a polynomial lattice. So a lattice whose elements are all pairs of polynomials, of rank 2 because they are pairs of polynomials. We call that a module, a rank 2 module, and it's generated by the basis 1H, 0Q. So I take a column-based element, a column-based vectors. So this lattice has a good property, which is it has a very small element in it. So if you look at lattices, if you take a random lattice, you expect all the short vectors to be about the same size. Well, in ntrue and in what we define as a module unique SVP of rank 2, you have one very short vector in one direction, like one very, very dense sublattice, submodule, and we have another one. So we get those non-typical shapes of modules. So this leads us to study more systematically those lattices, those modules. This is not coming up from nowhere, because lattices like that with one short vectors and another normal have been studied before. So that's the unique SVP problem, and it is known to be equivalent to bounded distance decoding and SIVP, at least quantumly. And so that's for unstructured lattice, like Z lattice. For R modules, so for polynomial lattices, well, this was not studied to our knowledge before. So we know that ntrue and module unique SVP of rank 2 are easier than module SIVP. Harder, I'm sorry. Than wait. I'm sorry. So we know that it is those problems are easier than module SIVP because there are instances of this one. We know since 2021 by Pelé-Marie and Stele that ntrue is easier than module SVP in rank 1. And that's about it. We don't know if all those problems in the middle are equivalent. Well, before that we didn't know. We don't know if module SVP of rank 1 is equivalent to ntrue. So that's what I'm going to present you today. So first, I will present an arrow from this one to this one, a reduction from module USVP of rank 2 to ntrue, showing that those two problems are equivalent. And then I will show you that the worst case of module USVP of rank 2 is equivalent to the average case. Okay. So first, module SVP of rank 2 is equal to ntrue. So our reduction works as follows. I give you some instance of module SVP of rank 2, and I want to transform it into some ntrue instance in order to make an ntrue solver running and to solve my beginning instance. So first, that's a bit of a technical detail. But for reduction to work, so we are given a basis of module USVP of rank 2 instance, which is basically a 2x2 matrix with polynomial entry, and I want those two polynomials to be co-prime. So in order to do that, what we are going to do is just to sample some small epsilon and to multiply our basis by the identity plus epsilon. Maybe we'll add some multiplicative factor, but basically, if we do that, we are going to change our basis and with high probability, well, probability that is, if you want to get into the details, approximately 1 over zeta k of 2 for k is the number field we're studying. This is going to make those two coprimes. Okay, so now I can suppose, eventually I will try again, that's easy to test if those two are coprimes. Eventually, when there are coprimes, I can get to the Hermite normal form. So the Hermite normal form is a quite classical thing to compute for a basis. It works for polynomials. It works for for those kind of things. So we are going to take the extended Euclidean algorithm in order to put a 1 here by column operation. So there exists A and B such that A B11 plus B B12 is equal to 1. So I make my columns operation, and I put a 1 here. Okay, so now I take a column operation to get rid of B12 in the column here, and I get this new basis. Okay, this basis is pretty similar to the entry matrix we had before, right? 1H, 0Q. The only big difference between the two is that B here is a polynomial, modulo x to the n plus 1, and Q here is an integer. So we want to transform this basis into some entro matrix. Okay, well, the way we do it is a bit brutal. So we take Q, we manage to have B is approximately equal to Q, and we multiply by Q over B, all the bottom line. So when we do, and then we round. When we do that, if Q and B are approximately the same, it doesn't change a lot the shape of the underlying module. And we even have an explicit formula for the short vector. So now we've got some intro instance. So H will be the rounding of A times Q over B. Q will be the modulus. And if we find a short vector of this in this intro instance, well, we've got a short vector into our previous instance. We won. Okay, we just transformed this basis, this modules, which is the same as our beginning module, into an intro instance. We can solve it, and we won. We solved the module USP in rank 2. Okay, so that's good. Now I have my reduction. But module USP of rank 2 is not just a module problem equivalent to intro, it also has group properties. So in cryptography, we like to have security based on worst case assumption. So for example, when we sample a key, the difficulty of breaking our scheme will be the difficulty of breaking a random instance of our problem. So what we want to do is to say, okay, I want to prove that there is a distribution in which I can sample the key, which is as difficult as the worst case instance. So how do we do that? Well, we are going to make a worst case to average case reduction. I take some worst case basis for module USP of rank 2. I'm going to shuffle it enough to make it random. Well, random meaning independent of the entry, of the input. And once it is independent from the input, then I can deshuffle and I can run my oracle and then deshuffle the solution in order to have back the worst case solution. So that's what I'm going to present now. So first, let's see the anatomy of module USP of rank 2 instance. So that's the QR factorization. Let's say that I have the best basis for my module USP of rank 2 instance. So I can make the QR factorization of this one, and it will look like that. One short vector, here, B1, and one very long vector, B2. And I can reduce B2 by B1 in order to make this R12 define modulo R11. So I have 4 variables, Q, which is a rotation, R11, R22, which are basically the length of our 2 vectors, and R12, which is the angle between the two. So the goal for the randomization is to randomize Q, R11, R22, and R12. The thing is, we don't have access to this basis, yeah, right? Because if we did, well, the problem will be solved. So first, I'm going to try to and randomize everything without the knowledge without access to it. So first, randomization of R11 and R22. How do I randomize R11 and R22? Basically, I want to multiply them by random primes. So first, I can multiply my whole module by a random prime. And okay, so R11 and R22 are going to be random, and I'm happy. But the thing is, they will not be they will not be randomized independently. So for example, if I multiply all my module by P, well, R11 divided by R22 will always be equal to the same thing. So I want to multiply R11 and not R22. This is going to be done by sparsification. So sparsification is something that has already been used in lattice-based cryptography and in reductions, for example, in the context of CVP reductions. So the idea is to say, I take a prime, and I'm going to choose at random a direction, and to keep only 1 point out of this prime. So if my prime is P, I am going to take 1 point out of P, and discard the others. So this is shown in this image. So I have this blue lattice, and I only keep the red dots. So we can prove that doing so, you don't change R22 that much with high probability, but you are going to have R11, which is the shortest vector of your sparsified lattice, is going to be multiplied by this prime that you choose. So you won. You multiplied R11 and not R22. So that's cool. Now we still have R12, so this angle, this thing to randomize. And the idea is the following. We are going to sample some Gaussian matrix, and to multiply on the left by it. So geometrically, what does it mean? It means that every point of the lattice is going to be shuffled a bit, not too far, in some direction. So basically, this is shown in this picture. This point is going to be moved a bit. You can do that mathematically, compute everything, etc. So what we do basically is we add some Gaussian noise into R12. But R12, as I said before, is defined modulo R11. So since R11 is a very short vector, which was our assumption with modulo unique SVP, right? Well, just adding a little Gaussian noise is going to be like uniform. Is going to make it not far statistically from uniform. So by adding some small noise, we make R12 uniform, and we even randomize the rotation matrix, since multiplying by a rotation matrix is and then wait on the other side. Multiplying by a Gaussian and rotation matrix is the same as multiplying by a Gaussian, and that's all. So here we won. We randomized R11, R22 in the previous slide. Here we just randomized R12 and Q in this slide. So we won. We've got worst case to average case reduction. Well, not exactly yet, because all the operation we did on our bad basis, on the basis we were given at the beginning. But maybe in the basis we have at the end, we have information about the randomization. Maybe we kept information, and so Oracle could use it. This is not perfectly independent of what happened before. And we can't use anymore thank you. We can't use anymore the Hermite normal form in order to discard everything, because now we multiplied by Gaussian, so we are in the continuous world. We don't have any more polynomials with coefficient in Z. We have to somehow round our module. So how are we going to do that? Well, we are going to do what we call Gaussian rounding, which is we are going to compute a basis of the dual of our module. We are going to compute this basis of that, and to sample 2 points in the dual, which are very orthogonal. Since those and we are going to take the matrix of those 2 points, and to multiply on the left by it. Since those points are orthogonal, this is going to not change the geometry of our lattice very much, because it is almost an identity matrix, right? And since we are in the dual of our lattice, well, multiplying on the left by those points is going to round everything, because of the definition of the dual. So doing so, this is an adaptation of the rounding in the Koendeboer, Alice Pellet-Marie, Leo Duca, and Benjamin Wesolowski's paper about auricular random walk, but generalized in 2 dimensions. So by doing so, we get a lattice module in with integer entries, and we can use Hermite normal form, and we lose every information we did along the way, and then we won. Now we have a real reduction from worst case to average case for modulo ZP of rank 2. Okay, so I did hide quite a lot of things. So first thing, we worked about number field all along, so you have to take care of some number theoretic stuff during the whole thing. The modules are not necessarily free, so you get to use a modulo ideal SVP solver in some case. This Hermite normal form step can take zeta k of 2 numbers of repetition, and in some cases zeta k of 2 is exponential in the degree of the field. So that's another thing. And I also hide polynomial losses and approximation factor and distribution analysis, which uses Rényi divergence and statistical distance, which was a bit complicated. So yeah, just so now what we showed is that all this blob of problems, so intro, modulo USP in rank 2, etc., all these things are equivalent. And so I leave you with some upfront problem. So first, we need ideal SVP oracle in order to make some reduction, which leads to a distribution for intro instances in which we can't really sample right now. So one thing would be to try and find a sampleable intro distribution with worst case hardness. The composability of reduction with the intro search decision from Pellet, Marie Stelle 21 is not yet proven. And for the most number theoretic guys and girls around here, determining which number fields verifies that zeta k of 2 is polynomial is not that easy. So thank you very much for your attention, and if you have any question, feel free to reach me.
We have time for one quick question. So I have, okay.
How do you find the quasi-orthogonal basis in the dual used for the rounding?
Are you speaking about this?
That one, the one after.
This step. Okay, so first we compute a basis for the with LLL for the dual. And then we sampled Gaussian with Gaussian sampling, 2 points that are quasi-orthogonal. So the first one is sampled very close, like centered around, I don't know, here it will be lambda 1, 0. And we sampled here. And the second is sampled very near to 0 lambda for some big lambda. And then we got 2 points that are almost orthogonal because they are very close to 1, 0 and 0, 1.
Thank you.
Welcome.
Can you come back to the slide on n true?
Yeah.
Yeah. So this one. So I'm a bit confused because in the original n true, this is not the ring we're using. We're using x to the n minus 1, and n is a prime. So I was wondering, does your work apply also to the actual n true or only to this variation?
Yeah, that's a good question. So here I chosen to present it for x to the n plus 1 for some power to cyclotomics. But our work generalizes to any number fields, actually. And we've got different losses and different running times depending on the discriminant of the number field, depending on I think that's just all, like the discriminant of the number field and the degree. So I presented for x to the 2 to the r plus 1, but it works for the original n true. It works for n true prime. It works for, I don't know, multi-quadratic n true if such thing exists.
Okay, thanks for the clarification. So let's thank the speaker again.
Thank you very much.
Okay, so our next talk is going to be given online. It's about a non-heuristic approach to time-space trade-off and optimization for BKW by Hanlin Liu and Yu Yu. And the talk will be given by Hanlin.
Thanks for your introduction. Hello, everyone. I'm Hanlin Liu from Shanghai Jiao Tong University. Today, I'm presenting our work on the BKW algorithm. This is joint work with my advisor, Professor Yu Yu. The LPM problem has two versions, the search LPM problem and the decisional LPM problem. The search LPM problem is to figure out the secret X, given the public matrix A and the noise code word Y. Both the public matrix A and the secret X are uniformly random. The noise E needs to be sparse. It follows component-wise independent Bernoulli distribution. In cryptography, more attention is paid to the decisional LPM problem, which is to distinguish LPM sample and random sample. Two versions are polynomial equivalent. The hardness of the LPM problems varies based on the noise real. In the standard LPM problem, the noise real is constant, meaning that it is independent of the dimension. The best known attack is the BKW algorithm. The BKW algorithm is the first substantial algorithm to solve the constant noise LPM problem. Both the time and the sample complexity are 2 to n over log n. The huge sample complexity limits the application of the BKW algorithm. So Lubachevsky reduced the sample complexity to a smaller polynomial. However, the time complexity is increased to 2 to n over log n. We mainly focus on optimizing the BKW algorithm, and the low noise LPM problems is not the focus of our paper. Here, we recall the process of the BKW algorithm. Suppose that we have the LPM samples. The matrix is a random matrix A, and the next dark color is the noise code word AX plus E. First, we can divide the LPM samples into different groups based on the value of the first B bits of the matrix A. There are 2 to the B different groups. In each group, the first B of the coefficients have the same value. Secondly, for each group, we XOR the first row with the rest rows, so that the first B bits of the coefficients are all 0. Finally, we merge all results, so we can get the LPM samples with a reduced dimension and double noise. Double noise means that the resulting noise is XOR of 2 previous noise. Moreover, by doing, we lose the 2 to B samples, because in each group, the first samples is dropped out, and there are 2 to B different groups. All we show is the first iteration. In each iteration, the dimension of the LPM problem is reduced by B bits and double noise. We can do n over B iterations and reduce the dimension of the LPM problems to 1. We summarize the the main idea of the BKW algorithm. After n over B iterations, we figure out 2 to n over B vectors, which sum up to a unit vector. And the final noise is the sum of 2 to n over B initial noise. The final noise is so huge, and we need to repeat the above process many times on the fresh new samples. The fresh new samples can guarantee that the independence of the final noise. Finally, we do a majority votes to figure out the first bit of the secret. The process of recovering the other bit of the secret is likewise. For example, we analyze the complexity of the BKW algorithm to solve the LPM problems with a constant noise. Space complexity is 2 to b. Both the time and the sample complexity are 2 to b times 2 to n over log n. In order to minimize the time complexity, we have to set b as n over log n to make two terms in the sum odd. So the time and the space complexity all keep 2 to n over log n. Actually, there are some questions. First, the BKW algorithm has a huge space and a sample complexity, so the BKW algorithm will benefit from some trade-off to make it more practical. For example, time-space trade-off and the time samples trade-off. Question number 2, there are enough walls in the first step, but the walls are not independent. In order to get independent walls, the BKW algorithm needs to repeat the first step many times. So, how to remove the repeat step and save the corresponding fact? Recently, Asel et al. Proposed the time-space trade-off for the BKW algorithm. We record the process of this trade-off. First, we pick C-1 rules from the LPM samples and XOR them together. Secondly, we figure out another samples whose first bits have the same value as the result of the first sample step. Finally, we XOR two samples to get a new samples and loop many times to get enough new samples. All we showed is the first iteration. In each iteration, the dimension is reduced by b bits, and the resulting noise is the sum of c previous noise. Notice that the resulting samples are not mutually independent. So, they introduced an independence heuristic to fix it. After many iterations, we reduced the dimension of LPM problems to 1, so that we can discover the corresponding. Who did it? This algorithm is called the Lev-C-sum BKW algorithm. They optimize it by decisional technique and quantum algorithm. The main contribution of our work is a framework to optimize the BKW algorithm. Compared with a single list in the original BKW algorithm, we have many lists. These lists are mutually independent. Within each list, we only require that all vectors are pairwise independent. The rest of steps are the same as the original BKW algorithm. We prove that the pairwise independent will preserve from all leaves down to root. Thanks to the pairwise independent, they can analyze the complexity of our algorithm without using any heuristic. At the same time, our algorithm does not need to repeat step, and only do majority vote in the list L in the list 2-1. So we reduce the time complexity of the original BKW algorithm by a substantial factor. We give an example to show how to preserve the pairwise independent. Suppose the list L0I are mutually independent, and within each list, all vectors are pairwise independent. It is easy to show So we know that within list L11, all vectors are also pairwise independent. It is easy to show that if the size of list L0I are not less than 2 to b plus 1 over c minus 1. So by Chebyshev inequality, the size of list L11 have the sum bound. We showed that all lists in the second level are also mutually independent because the third lists are mutually independent. Using the sum wheel, we can analyze the Hamming weight of the noise from all leaves down to the root. So we only do the majority vote in the list L21 to recover the secret of LPM. With the help of our framework, we get a sum result as the work of Essel et al., but without using any heuristic. We introduced the C to do the time space trade-off. If the C equal to 2, then the complexity of our algorithm is the same as that of the original BKW algorithm. If we increase the C, we get a large time space, a larger time complexity, and a smaller space complexity. We can also use the decision technique and the quantum algorithm to further optimize our algorithm. Beta is also used to adjusting the time-space trade-off. Our algorithm can optimize the time-space complexity of the original BKW algorithm. We compare of our algorithm and with the original BKW algorithm and the recent work of David Das et al. We can save a sub-exponential factor. Lubachevsky introduced a sample amplifier to reduce the sample complexity to a smaller polynomial, such as n over n to 1 plus epsilon, while epsilon is a constant. First, they randomly pick many W triples from n to 1 plus epsilon sample. Secondly, XOR each W triples as a real LPN sample. By leftover hash lemma, when set W is equal to n over log n, then the new LPN sample is very close to the real LPN sample. Finally, invoke the original BKW algorithm to recover the secret of the LPN problem. Our sample amplifier is a little different. First, we split the LPN sample into a log n group, and each group has the same size. Second, for each group, we pick all W triples and XOR each W triples. So we get each list from each group. Then the lists are mutually independent, and within each list, all vectors are pairwise independent. W is equal to n over log n times log n in our algorithm. Finally, we invoke our optimized two-sum BKW algorithm to recover the secret of LPN problem. Compare with the Lubachevsky trade-off, we can save a sub-exponential factor. This is all. Thank you.
For one quick question. Okay, so let's thank the speaker again. The final talk of this session is Improving Bounds on Elliptic Curve Hidden Number Problem for ECDH Key Exchange by Junsu, Santanu Sarkar, Huaxiong Wang, and Lei Hu. And the talk, I believe, will be given by Junsu.
Hello, everyone. Thank you for introduction. My name is Junxu. I'm from Institute of Information Engineering, Chinese Academy of Science. The co-authors are Santanu Sarkar, Huaxiong Wang, and Lei Hu. Now let me talk about our paper. The title is Improving Bounds on Elliptical Curve Hidden Number Problem, for short, ECHMP for ECDH Key Exchange. ECHMP can be first introduced by Dambulla, Pallavi, and Hargrave at Aaron 2001 in order to expect the result of bit security for ECDH. At PKC 2017, Shining introduced a Diffie-Hellman version of ECHMP called ECHMP-X or Chinese ECHMP. Shining obtained the first rigorous bit security result of ECDH on a fixed curve. Similar to HMP, Chinese ECHMP can be used for cryptanalysis of ECDH key exchange in the case of side channel attacks. Now, let me introduce the definition of ECHMP-X for a given elliptical curve over prime field, a given point R. So R is public, and a positive delta, and let P is a hidden point in a given elliptical curve. Let the O oracle output M and outputs the delta MSB of the X coordinate of P plus M multiply R. So we know the partial information of hidden point P plus M multiply M. The goal is to recall the hidden point P given the current access to the oracle O. The notation delta over log P means the output fraction of X coordinate bit per iteration. And the previous result at PKC 2017, a rigorous bound 506 was put forward using a direct lattice method. At DCC paper, a heuristic bound 1/2 was given using the Coppersmith method. Clearly, the 1/2 bound is better. So the question is how to improve the 1/2 bound. In this worker, we give the following result. Let D be any given positive integer given enough large prime. The ECHMP problem can be heuristically solved when the bound is 1/d plus 1. Our method is a polynomial time in the log P for the any constant D. When D greater than 1, the bound, our bound 1/d plus 1 is better. Furtherly, we showed that one can heuristically compute all the bits for a given elliptical curve over the prime field if the oracle outputs any constant fraction of the MSB of the X coordinate. However, in the previous work, only for some constant function, such as PKC gives 5/6, GCC gives 1/2. Now, let me introduce how to transform this problem from Chinese Asiacrypt to the modular polymers. Recall the x-coordinate of the hidden point P can be transformed into the problem of the finding the desired small root of the modular polymers Fi. Fi, the monomers is 1 x0, x0 square, yi, x0 square multiply yi, x0 square multiply yi. And where x0 is a common variable, the coefficients are knowing. The integers e0 and so on are unknowing. They are bound by a value big X. Big X is equals P/2 prime delta. The corresponding analysis was given by Shani at PKC. So our goal is to recover the desired root in the polynomial time such that the bound big X is as large as possible. For a fixed prime P, big X, the bound, becomes larger if and only if delta, the knowing bit delta, becomes small because of big X equals P/2 delta. We revised the Coppersmith method to solve the Chinese Asiacrypt. The Coppersmith method was proposed by Coppersmith in the 1996. The Coppersmith method has many applications, such as cryptanalysis of RSA, attack of pseudo-random number generator, and so on. In the Coppersmith method, they have an important notion of the helpful polymer. So G is a helpful polymer if its diagonal element is bound by the mode P2⁻D. So a helpful polymer is added to the lattice. It makes the Coppersmith condition easier to satisfy. In other words, the more helpful polymers, the larger the bound X. Compared to DCC paper, we construct enough helpful polymers. Concretely speaking, for a fixed tube G1, G2, and so on, we consider some linear combination of the following polymer. This polymer is a product of several original polymers. So the polymer in the expression 2 are usually called shifter polymers in the Coppersmith method. So we construct some linear combination of the shifter polymers. And such linear combinations can be proved to be helpful polymers. Furthermore, the number of these helpful polymers is n choose D plus 1, which is a dominant in the total number. This is the key to our work. For example, a small example, given two original polymers, F1, F2, his monomer is 1, 0, x0, x0 square. yi, x0 multiply yi, x0 square multiply yi. We construct a linear combination of the following polynomials: f1, f2, f0 multiply f1, f0 multiply f2, y1 multiply f2, y2 multiply f1, f0 multiply f2 multiply y1, f0 multiply f1 multiply y2. So the possible monomers are divided two parts, the blue parts and the red parts. In the linear combination, the monomers with red color are missing. In other words, the red parts are disappeared. So in the linear combination, they are monomers are 1, x0, y1, x0 multiply y1, y2, x0 multiply y2, y1 multiply y2. The leading term is y1, y2. And let me give a lattice for this example. We construct a triangle basis matrix. This is seven polynomials, where the G7 is above linear combination. So the lattice L is bound by the coefficient vector of Gi, I from 1 to 7. We can compute the lattice. A determinant is equals p to power 6 multiply big X multiply 2 power 9. The dimension is 7. Based on the Coppersmith condition, we get the bound big X is smaller than p to power 1 over 9. Note that the diagonal element of G7, diagonal element is big X squared is smaller than p to power 2 over 9. This is smaller than p. So G7 is a helpful polynomial. We used enough helpful polynomial and get the final bound is big X is smaller than p to power 1 minus 1 over d plus 1 because of X equals p over 2 to delta. In other words, delta over log p is greater than 1 over d plus 1 for any positive integer d. But the best bound from DCC paper is big X is smaller than p to power 1 minus 1 over 2. It means delta over log p is greater than 1 over 2. So this works bound is significantly better than DCC paper bound because d greater than 1. This bound is better than 1 over 2. But our method is a heuristic because to compute the desired root, we use the globular basis. In this process, we need the following assumption. And this assumption is the zero-dimension ideal. It means these polynomials are common roots. The number of common roots is finite. This is a typical assumption for the Coppersmith method. In this paper, we justify the the heuristics by the experiments use the small dimension of lattice. So, conclusion, we significantly improved the bound for the 7 Shelley's ECHMP. Because of heuristic in the optimism method, we did not get the rigorous bit security result. That's all. Thank you for your attention.
We have time for one question. Okay, so let's thank the speaker again.
Thank you.
So we were a bit late at the beginning, but the last 2 online talks gave us a lot of time, so we can have the break now.
Hi, ladies and gentlemen. Before this session, I'd like to announce a few things. First, if you are vegetarian or have arranged to eat vegetarian, please, after 5 o'clock and before the banquet, come to the reception and pick up a marker that says vegetarian. Then you will be served with a vegetarian set meal during the banquet. Second, the banquet will be in the grand ballroom. Okay, I mean the website says to be announced, but both the schedule outside and all the other stuff says grand ballroom is here. Finally, the excursion. If you signed up for the excursion, and we are starting to collect people from 1:30 in the afternoon. Okay, so if you are coming, then starting from 1:30, we are collecting people until about 2:15. Okay, so if you eat too slow, you may not make it. And we urge you to eat quickly. And so basically, as soon as we collect 27 people, we send out a bus. Okay, so that's it. We turn this to the session chair. Apologies.
Okay, so welcome to the signatures session, the second session this morning, that will consist of 4 talks. So the first talk is going to be on rejection sampling in Lubachevsky's signature scheme by Julien Devet, Omar Fauzi, Alain Pasleg, et Damien Stélé. And Julien is going to give the talk. Please go ahead.
Hello. So thank you for the introduction. So this is joint work with Omar Fauzi, Alain Pasleg, Damien Stélé. And this time you'll understand what we meant with the target and plastic gun in the abstract video. So just to briefly summarize the work, what we tried to do is optimize the Fiat-Shamir with a board paradigm in the lattice setting. We basically tried to optimize everything we could think of, so the runtime and the signature sizes. We did so by formally studying how rejection sampling is used in this setting. And spoiler alerts, here are our results. So basically, runtime is optimal, and compactness, we have some lower bounds and how to reach them because they were not reached. And last question is why we were interested in this in the first place. So generic motivation is dilithium, which is a future PQ standard from the NIST. It's implementing this Fiat-Shamir with boards paradigm. And more broadly, rejection sampling is an interesting technique that's been used in cryptography in lots of different places. So we thought that it could be interesting to open the black box to see how it was working and if it was actually suited to our needs. So I'm going to briefly recall the signature scheme. Then I'll move to how we minimize the number of rejects, so how to optimize the runtime. And then I'll show you how to minimize the signature size. Okay, so let's start with the signature scheme, which will be a bit more generic than what you could have seen before. So the scheme is relying on the short integer solution problem. The most important thing here is basically that this problem relies on the shortness of some vector. And the smaller this vector is, the smaller the bound beta is, well, the harder the problems become. It will have some effect in the following of the talk. So let's go. Here's the key generation algorithm. You take a random matrix A, a small matrix S for some meaning of small, and you get the secret key. The verification key will be A and an A times S. Okay. The signing algorithm asks you to first take a short vector Y from some generic distribution. So that's where we'll be able then to play by changing the distribution Q will get different signature sizes. So it's really important. And then you have the following formula for the signature. Most importantly, so you're going to compute some challenge C, and the answer to the challenge is the vector Z, which is Y plus S times C. I don't have really time nor the need to show you the verification algorithm, but the only thing you need to know is that as long as this vector Z has some bounded norm, then we can make a verification algorithm that makes the scheme correct. If you want some concrete instantiation, well, previous works instantiated Q with Gaussian distributions, or what I will call hypercube uniform distributions. And if we keep it like that, then the scheme is not secure, okay? Because we don't have aborts yet. And as you can see, Z is leaking the secret key. So ideally, what we would like to have is to make sure that Z is independent from the secret. So we would like Z to follow some kind of target distribution P, which is independent from S. And there are two main ways to achieve that. The first technique is flooding. If you take Q with a very large standard deviation, then the shift S times C is almost unnoticeable. And then, Z is almost independent from the secret. But then you get a very large gamma, which basically drives the size of the signature. So that's not what we want. The other technique that we will discuss is rejection sampling. But in both cases, as soon as the signature is uncorrelated with the secret key, then it basically means that you cannot query the signature algorithm, because those signatures are uninteresting. And then the signature is secure. Okay. So now let's move to how we use rejection sampling, how it's defined and everything. So in the following, I will give some kind of broader setting which can apply to actually anything, and it can be not related to signatures. So the broader context is as follows. I give you access to lots of samples that all follows the same source distribution, and your task is to find any sample that is following some target distribution. And of course, you want to use as few samples as possible, because each sample will be one signature. And of course, you're not allowed to modify the samples, because those are signatures. So I mean, at some point you will verify them. So if you modify the signatures, maybe the verification algorithm will not pass anymore. And so while I explain how to do so, we will also see how to minimize the average number of samples you need, which basically drives the runtime of the signing algorithm in Lubashevsky's signature. So the technique, the generic technique, which we will call imperfect rejection sampling, is as follows. So you have the source distribution d tilde, and you're going to scale it by some factor m until almost all of the blue curve is over the green curve, okay? Then imperfect rejection sampling, it tells you, it can be seen as some kind of Monte Carlo technique. So you get a sample X, it gives you some abscissa, and with some probability, which represents sampling an ordinate, you will keep it or not. To keep it, you only keep it if it's under the green curve here, or else you restart. Okay? And you will get something that almost follows the distribution D, and hopefully it will be close enough. To study how big M must be, we introduce something that we call the smooth ring divergence. It can be seen as generalization of the Rényi divergence. There's a lot of math here, but it just means you take the smallest m possible such that everything up to some epsilon part is under the blue curve. Okay? We can take an example, for instance, to see what is going on. So if you take two Gaussian distributions, but one is slightly shifted with respect to the other, what you can do is remove the left part, the tail on the left, and then you can slightly shift the blue one until it's over the green one. And of course, the larger epsilon will be, the more of the tail you remove, and so the smaller m you will need to take. Okay, we actually have a concrete formula that we compute. It's just that it's a bit too big to write here. Okay, so then we studied how efficient this technique is. So first we look at the runtime. So we have this computation. So assuming that you are doing things correctly, so you took m big enough, then your average number of samples will be at most m over 1 minus epsilon. And if you focus on the case where epsilon is 0, then this is actually optimal. Even if you were to do different strategies, maybe go back to previous samples or whatever, this would not be faster. And we don't really have the same result for non-zero epsilon, but epsilon will typically be 2 to the minus 64, so it should, even if imperfect rejection sampling is not optimal, we don't think it's worth looking for a more optimal strategy. And something that will help me move to the next part is we study the quality of the resulting distribution, which is not exactly the target D. Previously, people looked at the statistical distance between the two distributions. We choose to look at the Renyi divergence because Renyi divergence is, in general, more helpful and leads to tighter security proofs in the case of signatures. So that's what we did. Okay. So now we move back to the signature and we move to a different topic because now we know that rejection sampling works and that it is quite fast. So we have the following optimization problem. Okay, I'm going to details all of those terms. So first, we are going to fix some value m. It represents actually how much resource you want to put inside the signature scheme. It will be the average number of rejects. And you want rejection sampling to work whatever shift you will have. So you need to take the maximum, you need to take m bigger than the maximum of all possible shifts that you will have, okay? Next is why do we take epsilon at most 1 over qs, which is the number of signature queries? It's because if you remember the quality analysis, when you plug in the fact that you will do QS signatures and everything, then you do the security proof. So you indeed find the tighter security proof with Renyi divergence rather than statistical distance, and it allows you to take epsilon a big O of 1 over QS. Okay. Then the first condition that we have here, if you remember, it's actually the condition that you need for correctness. Okay, so this defines the gamma, and actually you want to minimize it because it's really what drives the signature size. Because here we just omit the size of the challenge because it's just a hash, so we don't have really anything we can do on it. So we're just going to minimize gamma. And there is some kind of K-school effect because when you minimize gamma, if you remember, I said that the cis problem gets harder when you have a smaller bound. So you have a smaller gamma, cryptanalysis becomes harder, and then you can actually drop some dimensions or something to keep the same level of security, so it gets even better. Okay, and our lower bound is that when you take epsilon equals 0, then if you want to satisfy everything, you have the following lower bound, which is related to the maximal size of the bound of the shift. And we can now take a look at the choices of distributions that were done in previous works to see if they reach this lower bound or not. So the two choices that were made, if you remember, it's hypercube uniform, which is the choice made in dilithium, because you have an easy, it's easy to sample from ranges. It's easy to check if you have to reject or not, but you have bad compactness, And this compactness is not even scaling when epsilon grows. So it's not the distribution we are looking for. So maybe Gaussian is better because here it's a bit harder to sample and reject. You need to compute some exponential, etc. And actually, you can't use Gaussians in a perfect setting when epsilon is 0, so you don't reach the lower bound either. So we don't really know. We have a much better value. It's scaling very well with epsilon, but since we're starting from plus infinity, we don't know if this scaling is optimal or not. Okay? So we actually have a proposal, which is to use the uniform distribution in hyperboles. Because if we do so we see that when epsilon is 0, we reach the lower bound. And when epsilon, and it's actually scaling with epsilon at least as good as the Gaussian, so it's quite interesting. We also keep the deterministic rejection test, so that's like a good bonus. And to give you some intuition onto why we do this choice, well, it's because we are looking at Euclidean norms. So it's natural to replace hypercubes, which are fitting with infinite norm, with hyperboles, which are good for Euclidean norm. And also, it is scaling well with epsilon because we have some kind of nice geometry going on with hyperspherical caps or everything. And then to put things into perspective, we also looked at some practical parameters because just its asymptotics could not let us determine what was better between Gaussians and hyperboles. And actually, practical parameters don't help either because they are very similar. To compute these parameters, we based our computations on dilithium and the Gaussian variant. We introduced a hyperbole variant just for computations of sizes. And also those two last lines plugged all the improvements we've made in the computations. So we have larger epsilon. And also something I didn't say is that we slightly improved the computation of the smooth divergence for Gaussians, so we can take them a little bit smaller. Okay. To wrap things up, we have even more results in the paper. So for instance, we look at Bliss. We also have some kind of compromise between rejection sampling and flooding. And we also look at what we can do if we use continuous distributions, because then we have even more choices for P and Q. So we looked at whether that was interesting or not. So thank you for your attention. And if you have any question, I'll be happy to answer them.
So we do have plenty of time for questions. So maybe I'll start. So you have a concrete proposal for actually instantiating the sampling in so I guess it's the intersection between the Euclidean ball and the z to the n lattice.
So actually, when we looked at those sizes, so we are actually using, where is it? Okay. We are actually using the uniform continuous ball. And then when you want to instantiate that, indeed, you will, you have different ways of doing it. You can either just intersect with z to the n, or you can do some kind of discretization with maybe 1 over some big N, z to the n. And of course, the larger big N will be, the closer you will be to this optimal sizes from the uniform hyperbole.
Thank you. Any other questions? Okay, if not, then let's thank the speaker again. So our next talk is entitled Hawk. Module leap makes lattice signatures fast, compact, and simple. Oh no, sorry. It's Sphinx Plus. Oh, sorry. My apologies. So it's recovering the tight security proof of Sphinx Plus by Mikhail Kudinov, Andreas Hulsing, and Mikhail will give the talk.
Thank you very much for the introduction. So today I'm going to present a joint work with Andreas Hulsing on the recovering the tight security proof of Sphinx Plus. So first we will give a brief description of Sphinx Plus construction, and then we will analyze the security flaw in the previous proof of security of Sphinx Plus. Then we will discuss the key ideas that helps us to fix the proof. And we will finish our talk by analysis of hash functions and the properties used to prove the security of Sphinx. So for those who don't know, Sphinx Plus is a hash-based digital signature scheme. And it was recently chosen by NIST for standardization as a post-quantum alternative for signature schemes. The main reason why it was chosen, since it is a very conservative and a secure choice, and other signature schemes still rely on hashing, and in Sphinx Plus, nothing but a secure hash function is required. So during the third round, there was a security flaw found in the proof of security. This flaw didn't lead to an attack. There was still a non-tight proof which was still applicable. But using that proof will lead to around 60 bits of security loss. So our aim was to recover a tight security proof. And now we will discuss the Sphinx Plus construction, how different building blocks are combined to obtain a more effective scheme. And then we will come back to the security flaw and how we fixed it. So the first building block is a one-time signature scheme. Everything started with the Lampert scheme, which is a one-time signature scheme used to sign a 1 bit of information. You have two secret values which are hashed. The secret values form the secret key, the hash values form the public key, and to sign 1 bit of information, you just use corresponding part of the secret key. To verify the signature, you hash it and check if it is equal to the corresponding part of the public key. This can be expanded to get a signature scheme for n-bit messages, but then you will need 2 n-bit secret values. Winternitz found a way to optimize this. So in Lampert scheme, you have 2 hash values to sign 1 bit of information, and in Lampert scheme, you have 1 hash value to sign log W bits of information. So here we have L secret values. Each of them are used to form a hash chain. This is done by sequentially hashing the secret value W minus 1 times. And to sign the message, special encoding is performed, which is then represented as L values between 0 and W minus 1. And the signature reveals the corresponding blocks in each of the chains. To verify the signature, you again perform the encoding. It's a base W representation. That way you understand at which positions are the signature blocks, and you do the rest of the hashing to obtain the ends of the chains. Then you check if the ends of the chains are equal to the public key, and if it's so, then the signature is valid. So the main security idea behind the Watts signature is that if the attacker will forge the signature, he will need to find at least 1 block on a lower level in at least 1 chain. So the second building block is Merkle trees. So on the slide you can see how they're built. They are built from the leaves. You hash two values together, and you do so until you get to the root of the tree. In Sphinx Plus, the leaves are public keys of one-time signature scheme, in our case, SWATs. Yes, and another key feature of Merkle trees is authentication paths. Authentication paths contain nodes that help you to compute the root of the tree. So on this slide, you can see the purple leaf, and the authentication path for that leaf will contain the yellow nodes. So using Merkle trees, we can obtain multiple time signature scheme that allows us to sign the several messages. You use an instance of one-time signature to sign the message, and you also put the authentication path into the signature. But this is a stateful scheme. That means you have to keep track which instances you have already used, and you should not use them twice. Now we're ready to get the whole Sphinx Plus construction. So Merkle trees are combined in so-called hypertree. So you have different layers. And let's look at the top layer. There you have the Merkle tree, which is built from one-time signature instances. They are used to sign the roots of the Merkle trees on the lower level. And this goes on, for example, on the picture you can see 2 layers, but this can be more layers there. And the one-time signature instances from the bottom layer are used to sign few times signature public keys. So few times signature scheme is a stateless scheme where you can assign a few signatures. Usually, for example, in Sphinx, around 8 times you can use it, and then the security slowly decreases. And then few times signature scheme is then used to sign the message. So the digest of the message determines which instance of few times signature scheme is actually used. And then the signature contains the few times signature, the WATS signatures, and the corresponding authentication path. To check the signature, the verifier tries to compute the root of the Merkle tree at the top level, and if it's equal, then the signature is valid. So again, there was a security flaw in the proof, and the flaw was in the part that proof WATS security. So let's look at this in more details. So first, let's discuss how hashing is done in Sphinx Plus. Instead of using keyed hash functions, so-called tweakable hash functions are used. They take 3 inputs, public parameter, tweaks, and the message, and produce a digest. So the public parameter is a bit string that is a part of Sphinx Plus public key. And the same public parameter used in every tweakable hash function call for the same key pair. And yes, so the public parameter is there to separate different keys of different users, and this is a step towards multi-user security. Then the second parameter is tweak. The main idea of tweak is that it's different in every tweakable hash function call. So it helps to mitigate multi-target attacks, so it performs kind of a domain separation. So imagine we had only just one simple hash function to do all the hashing in Sphinx Plus. Then, for example, finding a pre-image for at least one value in this big construction would be much easier. And tweak helps us to separate these calls. So let's first take a look at the non-tied proof. First, the idea was the following. You guess what message will be asked for the signing query, and you place a pre-image challenge at the position of, in one chain at the position that you guess that the block will be, that you will need to reveal in the signing query. And then if there is a forgery, as we mentioned before, the adversary will have to reveal a block which is lower, so he will have to make a longer chain for that part of the signature. And there are 2 possible ways. Either the forgery will collide before your signature block, or it will collide afterwards. If it collides before, then we found a pre-image for that block. If it collides afterwards, this can be handled with a second pre-image resistance property. But yes, here the problem is that we have to guess which block we will have to reveal in the signature. And for one instance of what's the guessing probability is 1 over L times W. But in Sphinx Plus, we have a lot of instances of what's, and then we will have to guess not only the position in the instance, in the what's instance, but also which what's will be forged. So this is where the 60 bits loss of security comes from. So to avoid this guessing, the idea was to construct the whole chain from the second pre-image resistance challenges. And the idea was the following. Let's assume that the tweakable hash function has this property that for every output, we have 2 pre-images. Yes, real-world hash functions doesn't have this property, but there are ways to overcome this. And just for the ease of explanation, just assume that, yes, we have, for every output, we have 2 pre-images. And assume we have a perfect adversary that can find pre-images with 100% probability. Then, when I have my second pre-image resistance challenge, I can just submit the output to our pre-image finder, and with probability at least 1/2, he will produce the solution for our pre-image. This is due to the fact that the input that I already know is information theoretically hidden from the adversary. And this idea was used in the proof, and so we construct our chain with these second pre-image challenges, and hope that when the adversary will forge our signature, we will find a solution for the second pre-image resistance challenge. But the problem is now that since we have this chaining of hashes, the pre-image that we already know might not be hidden from the adversary. So assume the situation that one of the pre-images is in the range of hash function outputs and the second pre-image is not, then the adversary can determine which one you already know and give that solution to you. So yes, the key idea that helped us to obtain tight security proof was to observe that what's is used to sign the roots of the Merkle trees in the Sphinx structure. So the adversary doesn't have any control on those values. And that's why we can prove the security of what's in a Wickham model, which is called UNACMA. And in this model, the adversary has to perform all the signing queries before he sees the public key. So in this case, we don't have to guess anymore. We place pre-image challenges for each position in the chain. And again, there are 2 possible ways. Either the collision happens before the signature block, then we find the pre-image solution, or it happens afterwards. That we handle with multi-target target collision resistance, which can be viewed as, yes, second pre-image resistance kind, but yeah. Some of you may notice that due to our challenge placement, the distribution of the blocks and the public keys could have changed. This we handle with the notion called undetectability, which essentially declares that the output of a tweakable hash function on a random input is computationally indistinguishable from a random string. Another underlying problem in proving Sphinx Plus is that, again, in Sphinx Plus we have multiple instances of what's, and they all share the same public parameter, and some of them are used to sign the messages which are dependent on the what's public keys of other instances. And since we cannot, we don't know the public parameter until we place all the challenges, we cannot compute those dependencies just as it is. So we introduce a th lambda oracle, which is initialized with the same public parameter as in the challenges. And the adversary can query this oracle with tweaks and messages, but there are restrictions. The adversary cannot query it with the same tweaks that are used in the challenges. So the idea behind this is that we allow the adversary to query our tweakable hash function, but only for the tweaks that are not useful for the challenges. So this can be viewed as querying just independent hash function. So on the slide you can see the final theorems. We proved these multiple instances of what's security, and then when we proved it, we could just plug in that part in the Sphinx Plus security. The rest of the proof remained the same. On the slide you can also see there is a W factor in front of undetectability notion. This is due to the hybrid argument, but the W is usually a small value, which is either 16, maybe 256 at most. So this is just a tiny loss. Another important thing that we did is we updated the status of security properties. In our proof, we're using non-standard properties like typical collision resistance or pre-image resistance for one target. We're using more complex ones. So we have to analyze how hard it will be for the adversary to break them. To do so, we analyze how hard it will be to break such properties for random functions. And we update the bounds for multi-target target collision resistance and the multi-target undetectability. Another thing to look at is the constructions of tweakable hash functions. So tweakable hash functions, that Sphinx Plus proposed two possible constructions of tweakable hash functions from keyed hash functions. And there was an analysis, what are the requirements on the keyed hash functions to obtain the needed properties of tweakable hash functions. But Sphinx Plus didn't use pre-image resistance and detectability in their proof, so we also had to complete this part. So yes, in our work we recovered the tight proof of security for Sphinx Plus. We updated the quantum generic security of used properties for multi-target target collision resistance and multi-target undetectability. We also analyzed the constructions of tweakable hash functions and the connections between the properties. And some ideas for the future work is that they can be done a computer-aided proof. And so my colleagues already done a crucial part of security proof and verified. So the update is already verified in Asiacrypt. And also what you could do is you could analyze the used properties regarding the hash function construction, maybe Merkle-Damgrad, maybe sponge functions. So, and analyze what are the requirements there to obtain the needed properties. So thank you for your attention. Any questions?
So we have time for questions. Anyone? We don't seem to have any questions, so let's thank the speaker again. Okay, so this time the next talk is going to be Hawk. So Module Leap makes lazy signatures fast, compact, and simple. The paper is by Leo Ducas, Iman Postelwaith, Ludo Poules, and Wessel van Worden, and Ludo is going to give the talk.
Hi. Okay. Yeah, I will talk about the signature scheme, and it's based on module version of the lattice isomorphism problem. So first, let's start off with the NIST-PQC signature finalists. Of these, Falcon is the smallest, but despite this, NIST still recommended the lithium. Yeah, why is this? So Falcon, it's a hash and sign signature scheme. And what this means is that for signing, you have a message You hash this message to some target in a lattice, or just in a space, and then signing is sampling a nearby lattice point with a good basis, trapdoor basis. And then verification is checking that the same target you acquire is, first of all, in the lattice. And you can check this with a bad basis. And then you check if this target is close to the signature. And yeah, so it has small keys and signatures, Falcon. However, this sampling step in signing, that's a bit complicated because this requires high precision floats for the discrete Gaussian step they use. And if you want to emulate these floats, so this is on constrained devices that don't have floating point support, this emulation step is quite slow, and that gives a slowdown for Falcon on these devices. And also, if you want to mask this kind of stuff, it also becomes difficult. And this comes from the fact of the class of lattices they use, the entry lattices. And yeah, what was kind of the starting point for a project was that we just wanted to have like an easy lattice to sample from, such as z to the n, the integer lattice, and this is almost like the easiest lattice you can think of to sample from. However, everybody knows the good basis on the integer lattice. So how can you build a signature scheme out of this? That's a good question. So our idea was to hide the integer lattice by a rotation and make this rotation public. So this is kind of the normal picture. On the left you have the trapdoor basis in green, and on the right you construct the bad basis, red, and that becomes the public key. But now this good basis is not a secret key anymore, but instead we rotate the public key, and now the secret key is the rotation that is used. Right. And so the security is based now on the lattice isomorphism problem. And this is when you know that two lattices are isomorphic, and you have some basis that describes them. You have to find the rotation that maps one lattice to the other. And in terms of bases, this becomes this equation where you have to find also a unimodular transformation, U, that maps one basis to the other after the rotation. So now it seems like the problem has become worse. We introduced more floating point numbers in the rotation. Therefore, also B prime also has floating points. But we can also fix this by making this embedding implicit. So this B prime, we don't actually make this a public key. Keep it implicit, but we keep the geometry of the lattice. And what I mean with this is that we look at the gram matrix of B prime. So if you perform a rotation of your lattice, this gram matrix containing all the inner products of the basis vectors, this stays the same, as you can see. And this gram matrix can be made public. And this transformation is now kept as a secret. And when you ever want to get back to the basis described by this Q prime, you can take the Cholesky decomposition. This is giving you a basis that is upper triangular if you use column notation. And there was a previous work in last Asiacrypt that showed a generic way to, if you have a lattice where you can sample from, they provide a way to make a signature scheme on this lattice, where the security is based on some variant of lib, where you have to decide if some lattice is isomorphic to one or the other. However, yeah, so in the case of z to the n here, the secret key is this transformation, and the public key is then U transpose times U. because the initial basis was the identity matrix. So it becomes somewhat simpler. But the question is now to make this previous work competitive to the other NIST candidates. That's where this work comes in. So how do you do this? What are the steps? So first of all, we had to add extra structure to the integer lattice. And so we add a ring structure to it, and that makes everything better. We also have some compression techniques we used on the keys and also on the signature. And last but not least, we hash two targets in half the integer lattice. And this allows us to use two samplers. So one for Z and one for Z plus a half. And this is quite a major improvement because then you have a constant time sampler. You sample just from both. And then depending on which one you needed, you actually use. So yeah, that gives quite a speed up in practice. So first point, the extra structure, that we go to a ring version, and we don't take a module of rank 1, but of rank 2. So we do the standard trick of taking a cyclotomic ring of power of 2 degree. And here the secret, the unimodular transformation is 2 basis vectors, so they're all live in a ring. The first, the small f and g, are sampled from a discrete Gaussian with a small sigma. And then to find the capital F and G, we want to complete this matrix by solving the Andrew equation. And this determinant has to be 1 to make it an invertible matrix. And the solving this equation was actually done before. So we can use Falcon's key generation code and apply it to our case by only changing what they had a prime q. We change that to 1. So it kind of loses its meaning in our case. Also because we don't use a q-ary lattice anymore, but the integer lattice. And now, yeah, this public key is taken by u star u, and you kind of can think about this star as being the transpose in the module case. So next step, compression. Also, like Falcon, we can drop one of the secret key parts, the capital G, because the determinant was 1 in our case. And in the public key, we now have a 2x2 matrix, and this may sound big, but we have a symmetry property, so we can drop 1 of the 4. And then we can also drop the Q11, and this is because the determinant of U was 1. Also, the determinant of this quadratic form Q is 1. And that allows us to drop this Q11 as well. So now you only have half left. And we can also drop half of the signature. And this can be done by a round-off algorithm. So from Hessian sign, the signature is a nearby lattice point. And if we have fixed half of the signature, the other part of the signature has to be some lattice point that makes the signature close to the target. And this can be used in verification. And what's more important is that we can also do this only with the public data available, so only with the quadratic form and not with the transformation. So let's go into that. So how signing works exactly is that we hash a message to a target, and this H is then a bit string of length 2n, and this becomes an element of the ring by seeing it as a polynomial of length n, and then you have 2 copies of this. And then you sample a lattice point, so x that is close to, what is this, u times h over 2. So h over 2 is the target when you multiply it with u. So then if you take the u inverse again, this gives you the coefficients describing the point that's nearby. And what you can see now is, so u times s is close to a half u times h. And if you fix s1, this makes s0 times u0 has to be close to this thing here. And for this, we know how to do this reasonably well. So you have the round-off algorithm over the nearest plane. And we use the round-off. So if you do the math, you get this formula. You have to round some quantity. And although this u was secret, this q is public. So this can be done in verification. And what we had to do here is reject some bad key pairs where this q00 was too small. And that made it like this, this round-off made it fail like once in a million times. So we had to reject these key pairs, and it was like 10% of the key pairs had to be rejected. And in that case, the recovery works practically always. And this halved like the signature size by 2, or I think even more than 2, because the distribution is a bit different between the small f and g and the capital F and G. So how does it perform? Yeah, we wrote implementation in C using some parts of Falcon. And this is isochronous, so almost constant time, except for the encoding and decoding of the signatures and public keys. And as you can see, so everything is almost like twice as fast as Falcon. And the signatures are 20% smaller. And this is in the case of a processor having AVX2 support. So that's like high-end devices or just normal desktop PCs. And so Falcon did worse when there's no floating point support on the processor. And in that case, you get this performance. So because we only have to multiply things in this ring, with Hawk, we can use the entities in signing, but also in verification. And there we get this factor 15 speed up for signing. And yeah, this is even for the batched mode of Falcon. So Falcon considers this performance with signing in a case where you have a lot of signatures signed, and it kind of takes the average of this with some pre-computation on the secret key. And we haven't done this yet, but we still compare it. So if you take the unbatched version of Falcon, we have a factor 30 speed up. Yeah. So yeah, some remaining questions. First of all, maybe there are other lattices where you kind of can sample closer to a target and maybe get some smaller signatures or that kind of stuff. But then the main question is that we want more cryptanalysis on this lattice isomorphism problem and how it's like, are there reductions to other problems? So we know that if you solve SVP, you have the key recovery. But yeah, is there more? It's quite interesting to know. So to wrap up, I've shown a signature scheme that hides a rotation of Z to the n, and on this lattice, the sampling becomes easier, and we don't have to work with any floating points, and that makes it fast and compact. That's it. Thanks.
So, any questions?
Hear me? So it's a very good proposal, I guess. So, but compared to the Mitaka, so I like to ask 2 points. So in the Hawk, it can be parallel computation is possible. That's the first question. Second one is, what is your idea against side channel attacks?
Sorry, what was the first question? Parallel computation?
Parallelized. You mean that all computation is serialized computation. So you have any idea in parallel computation in how? No?
Sorry? What do you mean?
So in your implementation or performance verification, all operation is done by step. Okay?
Yeah.
So you don't have no idea on the parallel computation.
I guess you can do some sampling beforehand for every go set.
Okay.
That is possible.
Okay.
Yeah.
Okay, second question is any resistance against side channel attack? For instance, the constant time implementation or others?
We already have isochronous implementation. And it's basically we say this because that's more accurate than saying it's constant time, because this this signing is so fast that maybe some 10% is spent on encoding the signatures. And so technically it's not constant time because of this encoding, but this doesn't matter because these signatures become public, so anyone cannot learn more about how long this encoding took.
Okay, thank you.
Yeah.
Other questions?
Hi, thanks for the talk. So this looks a bit like what in MQ was done the whole time and what got Rainbow broken, like many schemes, because they also relied on the isomorphism of polynomials problem. So do you have any idea of how secure this lattice isomorphism problem is?
Yeah, so we know it's broken for codes, but for lattices, this kind of popped up, I think, 1 year or 2 years ago, that it's already quite difficult to do in dimension 9, where Wessel, he computed a lot of different lattices, and he wanted to know if they were isomorphic. This was quite difficult, he seemed. So it looks more promising than these attacks on codes and that kind of stuff.
Okay, so you don't have any reduction that shows that this is maybe as hard as some form of shortest vector problem or so?
No, we don't have these yet.
Thanks.
We still have a bit of time for questions, if there are more. Otherwise, let's thank the speaker again. Thank you very much. finally, the last talk of this session is going to be Bloom. Bimodal lattice, one out of many proofs and applications by Vadim Lubashevsky and Gokkan Yuan. And Kan is going to give the talk.
Check, mic check. Yeah. So yeah, thank you very much for the introduction, and thanks everyone for staying here. My name is Khan, and I'm going to talk about Bloom. Bimodal lattice, one out of many proofs and applications. So we have seen many lattice-based zero-knowledge frameworks in the recent years, and they usually, well, naturally they come with applications. For example, we had approximate proofs, or like Kashmir with boards, which was hinted in the first talk by Julian. And they naturally come with some nice applications. For example, the dilithium signature, and we also have like verifiable encryption, group signatures, and so on. And then, you know, in 2019, we had like algebraic exact proofs, and they also come with nice applications with exotic signatures, with much better signature sizes, and so on. And then, you know, then we had more and more frameworks with other applications where you just, in many cases, you can just substitute the framework like below, and then you get, because the framework itself is much better than before, then naturally these primitives, this privacy preserving applications, they are also more efficient than before. However, it's, you know, it's interesting, more interesting to kind of make use of the framework and not just use it in a black box manner. And that's kind of what we will show with the here. So in this paper, we show efficient one out of many proofs where we really make use of this, of the newest LMP22 framework from crypto this year. Well, another contribution is we show how to prove integer relations such as addition and multiplication. And the nice thing about this compared to previous works is that we don't need to commit to the carry vectors. And that's like a significant improvement. And also, well, because we had the name bimodal in the title, well, we used we improved this framework using bimodal Gaussians, but it's around 10 to 15% gain. And well, obviously one might think that all these, all these things are not really useful in real life. Well, I hope the music video has some impact in real life. But in this talk, I will only focus on the first bullet point. Okay, so let's start with some preliminaries. As hinted already in the previous talk, we will focus on these cyclotomic rings. So let RQ be ZQ of X modulo X to the D plus 1, where D is a power of 2. And then we define the automorphism sigma to be the one which maps X to the X inverse. So we have some weird definitions here, and I'll show you in the next few slides why they're interesting, hopefully. So yeah, so the next weird thing is that for a fixed number of variables, let's say k, I define this quadratic automorphic polynomial, this QA polynomial p, to be a function for which there exists a 2k variant quadratic polynomial t, such that p of m1 up to mk is equal to t of m1 sigma of m1, m2, sigma of m2, up to mk, sigma of mk. So informally, just think of these QA polynomials as just quadratic polynomials, but we also introduce some, there might be just some sigmas around. For example, m1 times m2 minus sigma of m3, or m1 times sigma of m1 minus x to the d over 2 plus 2. So, okay, so why are they useful? Okay, so that's for the next slide. So the simplified LNP22 framework can be, can be described like this. So suppose I want to prove knowledge of some short polynomials in RQ, M1 up to MK, which satisfy some relations. So for public QA polynomials P1 up to PL, we want to prove that for each I, PI of M1, M2 up to MK is equal to 0 over RQ. The second one is, let's say, more interesting, but it's also also not really intuitive. So for public QA polynomials P1 prime up to Pn prime, for each I, the constant coefficient of Pi prime of M1 up to Mk is equal to 0. So recall that Pi prime of M1 up to Mk is a polynomial over Rq, and we want to prove that the constant coefficient is equal to, let's say, 0. But because we are interested in zero knowledge, we don't want to reveal any information about the other coefficients. And then, yeah, the third thing is proving some various norm bounds. So we want to prove, if we want to prove some L2 norm, or we want to prove some binaries. Yeah. Okay, so so now, I guess maybe half or more, the majority of the audience here thinks like, well, what's the point of all these, of all the sigma? Why do we need sigma? Why do we need QA polynomials? Why am I here? And what time is the lunch? So, so I hope in the next slide I can explain a bit. So suppose I want to prove some basic relations over integers or over ZQ. For example, I want to prove binary. So I have a polynomial M. I want to prove that it has binary coefficients. So the first observation is that this is the case if and only if the inner product of M and M minus 1 is equal to 0 over integers. So basically, we would just want to prove this inner product relation. And then to prove that, we use the following lemma, which says that if we have the polynomial vectors x, y, then the constant coefficient of x transpose sigma of y is equal to this, exactly the inner product of these coefficient vectors x and y. This means in particular that if we want to prove the inner product, let's say, of M and M minus 1, we are interested in the constant coefficient of, okay, does it work? I'll just use my mouse. This is equivalent to showing that the constant coefficient of M, the constant coefficient of M times sigma of M minus the sum of monomials is equal to 0. Because the coefficient vector of M is M with an arrow, and the coefficient vector of M minus the sum of monomials is exactly M minus the 1 vector. So yeah, and for that we can just use the second bullet point of the framework. So that's the intuition. And similarly with proving linear relations, well, if I want to prove that the inner product of A and M is equal to U, for public A and U, then we just, using the lemma, we just need to prove that the constant coefficient of sigma of A times M minus U is equal to 0. Okay, so now we are ready to discuss the one out of many proofs. So intuitively, we can think of it as some set membership proof. So suppose we have some n values, T1 up to Tn, and well, in our case, we will pick n to be some base, beta to the L. So we want to prove that we know some opening M and R, such that for some index I, commitment of M and R is equal to Ti. And obviously, because we want it to be, well, we want the proof to be zero knowledge, so in particular, we don't want to reveal any information about the index I. So yeah, so it's time for some technical overview. Put the members in the matrix, call it U. So we put these values as the columns of that matrix, multiply by the selector, name it V. So we would define this vector V to be the binary vector which has 1 in the ith position. And that's a linear equation. It's easy to see. Well, now it's not really easy to see, but if we define a lattice-based commitment, then maybe it's a bit easier. So if we define the commitment to be AM plus BR, then the right-hand side is the matrix U, which consists of these columns T1, T2 up to Tn, times the selector vector, which has 1 in the ith position. So the right-hand side is just U times V. So we don't want to commit to it. That's linear size. So the vector V has length n. So we recall n is B to the L. So we tensor decompose into small VIs. So here the trick, which was used in the original paper by Grove and Kohlweiss, and then in matrix plus smile, and so on. The key idea is that if we have this vector I, which has exactly 1, 1, and all zeros in all the other places, then we can tensor decompose it into smaller vectors vi's, where each vi has length beta. It's binary and it has exactly 1, 1. So for example, yeah, it's a very small example. The 0, 1, 0, 0 vector can be decomposed as 1, 0, tensor 0, 1. So, okay, if I put M and R together and A and B together, then basically we just want to prove equations like AS is equal to U times V1 tensor, V2 tensor up to VL. So to do this, first we do the standard trick. Well, if I want to prove this equation, I will get the random vector as a challenge, and I will do the inner product and prove that the inner product is equal to 0. So what do we get? So what I describe is the first line of this equation, where the phi is this random vector, and then the second line is I will just move the matrices around from the left to right. So at the beginning, I had the U on the left-hand side. Now I have U on the right-hand side. The same with A. And then the third line is a little bit more complicated. So for the third line, we will use the following lemma, which says that if I have some vectors A and B, A has dimension n and B has dimension m, and W has length n times m, and I can write this as subvectors W1 up to Wn. Then the inner product of A tensor B with W is equal to the inner product of A and the matrix W1 transpose, W2 transpose up to Wn transpose times B. So it just, well, nothing too complicated. So to use this lemma, well, we set A to be V1. We set B to be V2 transpose, V2 tensor up to VL, yeah, to be B, and W is the U transpose phi. So that's so we get the U bar. Okay, so now the idea is that we'll commit, well, informally, we will commit to x1, which is that complicated term in the inner product, which is U bar times V2 tensor V3 up to VL. And then there are two things to prove. So, I mean, the first one is to prove well-formedness of x1. So we want to prove that x1 is indeed equal to U bar times V2 transpose tensor up to VL. And basically, we want to prove the equation, right? So we want to prove that 0 is equal to the inner product of V1 x1 minus S A transpose phi. So let's focus on the case beta is equal to D. So that we have these two equations to prove. And okay, so the second one, we can see that it's kind of equivalent to proving that the constant coefficient of sigma of V1 times x1 minus sigma of A transpose phi transpose S is equal to 0. Yeah, here I abuse the notation a bit because A transpose phi is a vector, but what I would do is I'll just map it to the polynomial vector and then take the transpose. Okay, but for the first one, well, it still looks complicated. However, it's kind of a very similar statement to what we are actually started from, and we can use the same idea by recursion. So now I had some x1, but later on I will get the x2, x3 up to x beta. It's a typo, but each of them has length d, or like beta. Oh, L, yeah. It should be L. So yeah, obviously we still need to prove, I don't know, that the S has short norm or the VIs have binary coefficients and all VIs have exactly 1, 1, but this can be covered by the framework. So if we just consider the soundness error, then, well, if this original statement wasn't true, then this inner product inner product check with a linear random combination, this equation would be true with probability at most 1 over q. So what happens if it's not negligible? For example, if q is 2 to the 64, then do we need to repeat it twice, which would be a bit costly? So we So let's set the base to be d over 2. And I will commit to the polynomials wi, for which the coefficient vector consists of the vi and the 0. So let's look at the right-hand side of the slide. So I have the w1, the coefficient vector, the first part of the coefficient vector is v1, and the rest is zeros. And the nice thing of that, which we will use, is that if I multiply w1 with x to the d over 2, then the second part will shift to the first part, but with the minus, but it's still 0. And then the top part will move to the bottom part, so it will be v1. Okay, so let me just run the proof with two random vectors, phi0 and phi1. And I will end up with these two systems of equations. So let me just focus, and I will also commit to x1, which now contains x10 and x11. So we want to prove these four equations, so let's just go step by step. So let's start with the blue one. So what I claim is that the blue equation is equivalent to proving, is equivalent to the constant coefficient of this blue polynomial is equal to 0, which is sigma of w1 x1 minus sigma of A transpose phi 0 transpose S. And why is it the case? Well, the main observation is that the inner product of v1 x10 is equal to the inner product of w1 x1. So why? Because if we just look at the w1 and x1, the coefficient vectors of it, then the inner product will be exactly v1 times x10 plus 0 times x11, which is exactly what we wanted. And then to prove then we focus on the orange part. So I want to say that this orange equation is equivalent to the constant coefficient of the sigma of x to the d over 2 times w1 times x1 minus sigma of A transpose phi 1 transpose S is equal to 0. And here it's kind of similar idea. So we just need to show that the inner product of v1 and x11 is equal to the inner product of x to the d over 2 times w1 and x1. And we can see it here. So if we look at the coefficient vectors of x to the d over 2 times w1 and x1, then it's 0 times x10 plus v1 times x11. So yeah. And then to prove these things, we can just use the framework. So yes, the last part is the purple equations. Just by combining them, we can see that it's equivalent to x1 being u0 bar, u1 bar times v2 tensor, v3 tensor up to vl. And because we have one less tensor, we can just continue with the strategy with recursion. So yeah, just briefly about performance. I guess I'm out of time. So one of the many proofs can be used directly to build ring signatures and group signatures. This work, our scheme really scales well with big sizes, ring signature sizes. So even for around 2 to the 21, it's moderately better than SMILE and all the other falafel matrix and calamari. And the nice thing compared to the lattice ones is that we have very small public key sizes. So around 0.1 kilobytes. Just to showcase the integer relations proofs, thanks to the fact that we don't need to commit to these carry vectors, we get more than a factor of 2 improvement compared to the prior works. So yeah, thank you very much. And that concludes my talk.
So we have time for questions. So apparently people are hungry, so let's thank the speaker again.